dinosaurs. They once ruled the Earth. Why did they go extinct? The consensus is that an asteroid collided with the Earth. This theory emerged in 1980. But it wasn't immediately accepted by the scientific community.
Geologists had never witnessed a gigantic asteroid impact on the Earth. They could not accept that something that large and catastrophic could have happened in the past.
Scientists back then believed that species extinctions happened gradually due to climate change and other environmental changes, and the resulting natural selection. That's why the asteroid impact theory, an unfathomably huge natural disaster wiping out an entire species, was seen as unscientific and roundly rejected. Yet there were young scientists who had faith in this theory, but they weren't astronomers. They were unknown geologists.
It was new and exciting. It was certainly unknown if this theory was right, that there had been a large impact that had driven the dinosaurs extinct, and there was work to be done to answer this question.
There were some professors writing in the paper and telling, oh, this nonsense, this Jan Smith is telling, you know, that. And by now you realize it's in the children's books.
These geologists, specialists in the ground below, solved the mystery of an event that came from far in outer space and altered the course of life on Earth. What could possibly have happened 66 million years ago? And how did humankind come to find out? Here, we'll examine the unknown history behind this theory. Our journey to learn the truth behind the dinosaurs' extinction begins in Caravaca in the southeast of Spain. Its streets retain the look and history from medieval times. This is Dutch paleontologist Jan Smit. He made an important discovery that helped unlock the mystery of why the dinosaurs died out.
You see it. It has the name still on it. So 40 years ago, we slept here. It was the only hotel in town, and it had very high rooms, so it was always nice and cold inside, instead of being hot.
Smit first visited here in 1971. He was a university student at the time. His destination was this cliff. He came here to study a certain stratum layer that would soon become a focus of major attention. The layer marked with the yellow line is 66 million years old. Below this layer is rock from the Cretaceous period, when the dinosaurs ruled the Earth. But above it is from the Tertiary period, when mammals thrived. Taking the letters from Kreide, the German word for Cretaceous, and Tertiary, it was given the name KT boundary. One day, along this KT boundary, Smit noticed a strange phenomenon that defied conventional paleontological wisdom.
What we have here is the topmost Cretaceous. You see these big boulders, and if I take a small piece of this, the very top, and I take my hand lens, you can see all the big foraminifera still in there. And they're easy to spot here. And all of a sudden they disappear. Right at the bottom of this dark clay layer.
Smith specializes in the study of fossils from a certain ocean-dwelling creature, one that's not quite as glamorous as the dinosaurs. It's a kind of plankton called foraminifera. Even the largest don't measure 1 millimeter, but by taking a closer look at their shell shapes and sizes, we can estimate the ages of layers and changes in the environment. In a part of the layer in Spain, Smith found an unexpected distribution of foraminifera. He found that older Cretaceous layers contained considerable amounts of larger foraminifera, but when he got to the KT boundary, they suddenly disappeared.
We thought at that time, beginning of the 70s, evolution was slow and such sharp boundaries should not exist. But what I found in the field was always, boom, you can put a knife in the rocks. And then I started asking myself a question, how can that be? So sudden, there must be something wrong there. And that's what piqued my interest in the KT boundary. So I started looking for it. I had questions, why is it so sudden? But I had no answers whatsoever.
Right around this time, another study into the KT boundary was about to begin. It started in Gubbio, an old town in central Italy with steeply sloped streets. Here at the Contessa Quarry and other areas, there are limestone cliffs made of seabed sediment that hardened over 100 million years. This region offers many views of the KT boundary. See this layer of 1 centimeter rock sandwiched between thick limestone? This is the KT boundary. One scientist took special interest in this reddish-brown clay. His name is Walter Alvarez. He's a legendary geologist who proposed the bold idea that would come to be known as the Alvarez hypothesis. His research partner, Alessandro Montanari, recalls their time together.
In fact, the Alvarez, back in the mid-70s, was actually coming over here, even over this outcrop, every summer to study the evolution of the Apennine Mountains, the tectonic evolution of Apennine Mountains. And by doing so, though, he came upon this very intriguing issue of the boundary between these two eras, you know, the Mesozoic and the Cenozoic era.
However, no fossils turned up in the clay from the KT boundary, and no new information was gained. So Walter decided to approach his father, Louis Alvarez, for help. Louis was a world-renowned physicist. He won the Nobel Prize in Physics in 1968. He was also known for a wide range of ideas outside of physics, including his experiment that used cosmic rays to look inside the pyramids. Louis' protege Richard Muller recalls that time.
One thing that Louis Alvarez could not understand is what was so interesting about geology. He thought it was the most boring science you can imagine. Walter tried hard to intrigue him, and it didn't work until Walter brought him a present. It was a rock that he had carved out of the rock formation in Gubbio, Italy, and it showed something that was a puzzle, a real puzzle. Nothing intrigued Louis more than puzzles, and this was a revelation to him.
Inspired by his son to take interest in a totally different field, Louis came up with another new idea. He suggested that the amount of the trace element iridium detected in the rock layer could be an indicator of environmental changes. Iridium is extremely rare in rocks on the Earth's surface, but is much more prevalent in meteorites and other material from outer space. And it is constantly falling onto Earth, along with tiny dust particles. The seabed contains deposits of plankton shells and clay carried from the land. At the same time, iridium-enriched dust from space is supplied at a steady rate. If environmental changes led to a drop in plankton, the concentration of iridium should rise relative to this. If we could measure this iridium, which trickles down like sand in an hourglass, we could track changes in the Earth's environment. Back then, Luis Alvarez was working at the Lawrence Berkeley National Laboratory, managed by the University of California, Berkeley. This lab was the center of the nuclear physics research conducted by the United States in its struggle for supremacy with the Soviet Union. Colleagues who were world-leading experts in trace element analysis lent their support to the Alvarez father and son team. These videos are from 1978. Using state-of-the-art equipment, the scientists measured iridium in the rock layers. The results were astonishing. Concentration of iridium in the KT boundary reached 30 times that of the adjacent layers.
The samples that were coming from that very short little interval, in fact, they show a huge increase of extraterrestrial material. And that increase was too big. If they had to normalize it for the background signature, the time expressed by that clay layer will be longer than the entire section that they measure in this gorge. And that would have been possible.
What could have been the source of this iridium? Luis Alvarez first imagined a supernova explosion by a star that has reached the end of its life. That's because if a star near Earth had exploded about 66 million years ago, it would have showered the Earth with iridium. But that would have also produced plutonium, which was not found, and so this theory was rejected. Louis then turned his attention to the countless asteroids orbiting in the belt between Jupiter and Mars. When the orbit of an asteroid, which could measure up to tens of kilometers in diameter, changes due to a collision in space, and it collides with Earth, it becomes a meteorite. If an asteroid smashed into Earth, it would bring with it massive amounts of iridium. Assuming that the KT boundary layers around the world contained iridium, Louis estimated the meteorite's size.
The order of magnitude size of this meteorite came out to be 10 kilometers. 10 kilometers is like Mount Everest.
So this theory seemed to make sense, and they couldn't come up with any way to disprove it. They could not falsify it. It was the only one they could not rule out. And so they decided now's the time to publish. There's no alternative theory that we can come up with. Let's publish, and they did. And our understanding of evolution and life on Earth changed with that paper.
This became the Alvarez hypothesis, which was introduced in 1980. It posits that an asteroid 10 kilometers in diameter struck the Earth, creating massive clouds of dust with its impact. This caused massive environmental changes that led to the dinosaurs' extinction. However, the road to acceptance of this theory was hardly a smooth one. How did scientists react to this idea that overturned all conventional wisdom? At the time, Peter Ward was an up-and-coming paleontologist studying the era when the dinosaurs died out.
Geologists had never witnessed a gigantic asteroid impact on the Earth, and therefore, because they've never seen one in our lifetimes, they could not accept that something that large and catastrophic could have happened in the past. The asteroid impact theory, the Alvarez theory of 1980, brought the geological fraternity, if you will, the realization that the old idea of catastrophism perhaps was true after all. And there was great resistance to this.
However, the iridium that supports the asteroid impact theory was found in KT boundaries around the world. In Italy, then in Spain and Denmark, and on a Caribbean island and inland United States. Finding layers showing the same characteristics all over the world is extremely rare in geology. In 1981, Jan Smit wrote a doctoral thesis about the KT boundary in Spain and became an ardent supporter of the asteroid impact theory.
If you have an impact, what does it do? I'm not a specialist in that. So I started reading up, and the literature say if you have an impact, you have all sorts of ejecta which come out of the crater. And it's our task to find these sort of ejecta. So I started scribbling at that tiny layer at the base of the KT boundary, and I found tiny white spherules.
These are the spherules found by Smit at the KT boundary. They measure less than a millimeter each. An enlarged cross-section reveals mysterious, feather-like crystal shapes. This is the pattern that molten rock takes when it is suddenly cooled. Smit saw this as compelling evidence that a massive asteroid crashed into the Earth.
Not only from Spain, but also from Italy, because as it turned out, everywhere you go where there is the KT boundary, inside you find an iridium anomaly, but also these spherules.
However, conservative scientists resisted the asteroid impact theory. insisting that a volcanic eruption would have had the same effect. On their minds was the eruption of Mount St. Helens in the United States in 1980. This large and destructive eruption fueled the volcano theory. Giving further credence to this idea was the remnants of volcanic eruptions at the Deccan Plateau in India. These eruptions spewed huge amounts of lava at a time very close to when the dinosaurs died out. Were the dinosaurs wiped out by a huge asteroid's impact? Or was it a giant volcanic eruption? A fierce debate raged on. As the debate continued, one young man thought he could put a stop to the controversy. He was a graduate student named Alan Hildebrand.
When I started graduate school, this was a new idea and quite controversial. Many people were debating it. Some people thought, oh, there's no way that could happen. The people we got this very unusual evidence that an impact occurred. So naturally, you can debate with people all day long, but if you have no new evidence, this doesn't answer the question.
There was one flaw in the asteroid impact theory. The crater that such an impact would have made had never been found. Such a crater was estimated to measure 200 kilometers in diameter. If it were on land, no one could miss it. By that time, about 100 craters had been found, but none matched the size and time period the scientists were looking for. So Hildebrand decided to take a fresh look at the world's KT boundaries from a new perspective. In March 1987, he traveled to the KT boundary in Texas. Here he saw some features seen in no other KT boundary.
So 66 million years ago, where we're standing would be in the middle of the continental shelf, and we would have about 100 meters of water on top of us. And on the shelf, we're depositing just this fine-grained gray mud. And we see millions of years of this mud. And then right here, something extraordinary has happened. Something has come and eroded the seafloor and ripped up the sediment in the 100 meters of water. So this had to be a giant wave. And this deposit is different. We had the initial giant wave or waves eroded the seafloor, moved material, started dumping it. Then the smaller waves coming, moving the sediment, of course still very fast for this environment.
The KT boundary that was assumed to be 1 centimeter thick grew to 1 meter with the sediment from the wave. Perhaps this giant wave was produced by an asteroid impact. Hildebrand took this theory and went looking for the point of collision. He went from Texas to the Caribbean island of Haiti to narrow down the site candidates. His findings pointed to the Gulf of Mexico and the Caribbean Sea just south of the U.S. 10 years before Hildebrand conducted his survey, another geological survey was taking place on Mexico's Yucatan Peninsula, which separates the Gulf of Mexico and the Caribbean Sea. It was directed by a state-owned oil company. They were searching for new oil fields. They'd sent a team of experts with the latest technologies. Part of that team was Glenn Penfield, a specialist in resource exploration. In 1978, Penfield, who was 26 at the time, spent half a year in Mexico.
In the late 1970s and early 80s, we had very high quality airborne magnetometers. So the airborne magnetometer was good at finding basins where there might be a lot of sedimentary rock and oil because they weren't very magnetic.
His first survey was in the Gulf of Mexico, north of the Yucatan Peninsula. By examining the magnetic fields of rocks using sensors in airplanes, the seabed structure can be estimated. As he checked the data, one day Penfield noticed something unusual. Some locations caused big swings in the sensor's needle. When he entered those positions into his map, he found something completely unexpected. It formed a nearly perfect semicircular pattern. Its diameter was a staggering 180 kilometers, large enough to hold the entire American state of Connecticut. When he joined this arc with other topological data found in the 1950s, the land and sea patterns connected to form one big circle.
So I'd seen many, many volcanoes with high quality magnetic data. Knowing what the magnetic signature of that is, there was no way this could be volcanic. Totally different picture, much simpler, perfectly symmetrical on a very large scale.
What caused this pattern to form? Penfield, also an astronomer, came up with an idea. Inspired by the craters on the moon's surface, he thought that perhaps the same indentations could be found underground. His findings coincided with the Alvarez team's discovery of unusual amounts of iridium in the Italian KT boundary. But Penfield wasn't free to do his own research. He'd been sent to look for oil. He was working for the Mexico Petroleum Corporation, also known as Pemex. This kind of specific data was a trade secret for Pemex, so it could never be published in an academic paper.
In '81, I spoke to Alvarez and you know, they just said, "Oh, we all know it's volcanics. This kid doesn't even have a doctorate, or, you know, he's not worth talking to, some oil guy." Not a real scientist, just an oil finder.
There was no way to confirm the existence of this 66-million-year-old crater from above ground. Penfield's report stayed buried in mountains of documents at Pemex's headquarters in Mexico City. Despite the heated controversy surrounding the reason for the dinosaurs' extinction, no scientist laid eyes on the report. About 10 years later, in March 1990, Hildebrand had narrowed down the point of collision, but still couldn't locate the crater, so he made a phone call.
Hello, do you have a listing for Glenn Penfield? The last name is P-E-N.
The call was to Penfield.
Well, I guess when I got that first call, I was pretty happy. Like, finally, okay, somebody else is looking for this right in the neighborhood. I know where it is. So, yeah, this is good that they've constructed the evidence that the sediments associated with the impact appear to be thicker. They're looking for it right in this area, roughly the Caribbean or the Gulf of Mexico, and we know exactly where it is. So, yeah, that made me very happy to see that.
Penfield's discovery was reported in a newspaper just once, with special permission from Pemex. This was the article that led the two men to meet. An oil explorer and a passionate grad student. The two hit it off immediately. During his off time from Pemex, Penfield offered his support to Hildebrand. Using Penfield's knowledge of Spanish, they gathered evidence that the structure underground was in fact the crater.
This is more or less what we were looking for at Chicxulub.
Then they found the wells that Pemex had dug.
There's your data. Didn't find oil, which is what they were looking for, not craters, not the extinction of the dinosaurs, not one of the 3 or 4 main events in Earth history. Forget that. No oil. Cap it, walk away.
The two men hit upon the discovery that some of the underground rock dug up there had been sent to an American university.
So Glenn said, well, finding samples would be very important, so we should do that. So he supplied the bit of initiative to go after those samples, so I could look at them and find the sharp quartz in them, which gave us more evidence to start writing the second paper.
Researchers examining the rock under the Yucatan had found shocked quartz. These intersecting parallel black lines indicate that it had been subjected to a strong impact. This was the best evidence yet of the giant collision. In 1991, it became clear that the circular pattern Penfield had found was formed by an asteroid's impact. The region at its center had become a fishing village. The crater that altered the course of Earth's history was named after this village, Chicxulub.
I'll never be an astronaut and walk on the moon, but when I'm walking here, I picture I can mentally reconstruct it, and I'm walking across Copernicus or something on the moon with a little bit of earthly cover on it, some vegetation, a little bit of limestone, but it's right there under our feet.
A giant 180-kilometer crater that was formed 66 million years ago. This was the evidence that asteroid theory scientists were waiting for. Its size and age were just as they had predicted. 10 years after the discovery of iridium in the KT boundary, the final piece in the puzzle of the dinosaur extinction mystery had been found. This led to the acceptance of the asteroid impact theory. This led to the question, what impact did the asteroid collision have on the world as a whole?
It has some scarps in it, fault scarps. So it took Rosetta
One of the first to tackle this mystery was planetary scientist J. Melosh.
67P, looks just like a star.
He's an expert on catastrophic collisions, including the idea that 4.5 billion years ago, a Mars-sized object collided with Earth and formed the Moon, known as the giant impact hypothesis. When the Chicxulub crater was discovered, Melosh made a calculation.
The Alvarezes had proposed that the impact created a lot of dust that rose into the atmosphere and blocked the sunlight. While that was plausible, it seemed to me, when you think about it, the atmosphere is so thin in comparison to the size of the other things that the impact should have thrown things not just into the atmosphere, much higher, much farther.
The thickness of the atmosphere is 10 kilometers, just 0.1% the size of the Earth's diameter. His calculation showed that most of the high-temperature rock debris smashed through the atmosphere with the impact of the collision. And then, just hours later, without even time to cool down, the fireballs poured all over the Earth.
It also seemed that that amount of thermal radiation would probably kill any animal that couldn't find shelter, and that actually agreed pretty well with what we found for the pattern of extinctions, that it was the large-bodied animals that died, the dinosaurs, large birds. What didn't die were animals that lived in holes in the ground, our ancestors, the mammals, and crocodiles, snakes, frogs that could go underwater.
Huge amounts of heat were given off by the fireballs that showered the Earth. Then the dust that covered the atmosphere caused a massive cooling. Melosh believes that both of these events wiped out the dinosaurs. But that's not all. There may have been an even more terrifying event 66 million years ago.
And your thoughts?
At this university, the birthplace of Alvarez's theory, scientists are still looking for clues to determine the exact cause of the dinosaurs' extinction. They headed toward the site of a massive volcanic explosion. Their destination, the Deccan Plateau in India. This has been a special concern of volcano theory believers because of the eruption that occurred here right around the time the dinosaurs died out.
Yeah.
These cliffs are all made of lava. Their thickness reaches 3,200 meters. The area of the site is larger than all of Germany. A full-scale survey began here in 2014. It's been joined by scientists from India, the US, and Europe.
The scale of these lava flow fields are much larger, but you do find the same type of features. So these are 66 million year old rope texture, the same that you would find at the surface of a modern lava flow in Hawaii or Reunion Island.
One part of the Deccan Plateau gives a sense of just how massive the eruption was. It's a temple hollowed out from the lava rock cliffs. The survey team is here to look at the lava from which Buddha statues have been carved. Because it's carved so smoothly, it offers greater insight into the history of the eruption.
Features at the surface, but then individual units or individual lobes are 1 to 2 meters.
The team will spend 5 years surveying the entire Deccan Plateau. They want to understand the whole picture of what happened here. They took the lava they collected in India back to the university for further analysis. By measuring the amount of argon gas trapped in the lava, they can determine the time of the eruption to within a few tens of thousands of years. They are on the verge of a breakthrough that will give the world the clearest picture yet of the whole eruption. Then in 2015, yet another new discovery was made. The massive lava flow poured over a much larger area than originally thought, right when the Chicxulub crater was formed 66 million years ago. What impact did the asteroid have in the vicinity of its landing? That's another mystery being solved. This is Professor Joanna Morgan of Imperial College, London. She studies underground structures using artificial earthquakes.
So what you're looking at here is seismic reflection data across the Chicxulub impact crater. Here is the bottom of the crater floor, and you can see these lovely two hills here. This is our peak ring.
The raised parts along the bottom of the crater form the peak ring. The same sort of structure can be seen on the moon. You can see a ring of mountains on the inside of the crater. This is the peak ring. Just how it was formed was shrouded in mystery. Using his computer to explain this phenomenon is a researcher who was just 3 years old when the Alvarez hypothesis emerged. Gareth Collins. Here, he simulates the asteroid collision and the passage of time. A bowl-like crater is formed, and the reaction generates a huge mound in the center.
And what we see is we have this huge mountain in the center of the crater that's 5 to 10 kilometers high, so it's similar size to Mount Everest. We formed Mount Everest in 3 minutes.
Sometime later, the mountain collapses, and it gradually spreads out. On closer inspection, we see that the crater's inner ring has formed a peak ring. This peak ring, reproduced by the simulation, is very similar in both size and shape to the actual crater.
To understand the environmental consequences of the impact, about how much energy was released, how much dust was thrown up into the atmosphere, we really need to know how big was the asteroid that formed the crater. And numerical simulation allows us to do that.
In 2016, a new excavation took place at the Chicxulub crater. Jan Smit, who noticed the aberration at the KT boundary in Spain 40 years ago, also took part.
There are many people who ask me, why can you be busy for 40 years only with one subject? But if you look at it, this is the only scientific problem where all the sciences, the exact sciences, come together. Chemistry, biology, geology, physics, modeling. They all work on one project. That's the only unique, so to say, project.
And also observing the project is the man who stumbled upon the crater while looking for an oil well, Glenn Penfield.
The well will test much of that same section as those 60-year-old wells that we looked at, but of course with the latest tools and the latest science, the IODP has a magnificent collection of scientific tools to use, and so we're going to learn a lot more. That's why this place really should be the school book, the textbook of the world for studying impact craters. And I think it will be. We're just beginning to get at Chicxulub.
The asteroid impact of 66 million years ago is now an accepted fact. Most scientists believe the impact caused massive environmental changes and wiped out the dinosaurs. But this allowed the rise of the ancestors of humanity, the mammals. The asteroid collision set the conditions for the human race to thrive. It was the event that made our life on Earth possible. This cycle of extinction and prosperity could be the fate of all organisms on Earth. The likelihood of another 10-kilometer asteroid colliding with Earth is about 1 in 100 million years. But that's a chance we cannot afford to take. Scientists are working on ways to avoid the next collision and break the cycle.